Our first question today, as we're all talking about arc flash mitigation, is what is an arc flash? An arc flash is simply an explosive release of energy through the air phase or phase to phase or phase to ground. The NFPA states that temperatures of an arc flash can exceed 35 K and in fact have been tested to exceed 36,000 degrees Fahrenheit, which actually happens to be hotter than the surface of the sun. During an arc flash event, copper can expand up to 67,000 times its original volume and hurl shrapnel at over 700 miles per hour. So why do we need mitigation? Well, very simply, we want to protect the lives of whether it be our workforce, contractors, or visitors to our facilities when they're cleaning area, servicing gear, taking performance measurements, or in some cases, changing breakers, fuses, pulling wire. We want to protect the property that is within from arc flash damage events. The explosive nature obviously tends to rip through equipment and can cause significant damage from smoke, fire, and other shrapnel-related damage to adjacent electrical gear. We also want to protect our clients' uptime. In certain areas where uptime is critical, these events can destroy gear and can cause a facility to have to resort to temporary systems for days, even weeks, and may be difficult to implement even when the temporary systems are brought in. Now, our code considerations. Obviously, NFPA 70, the NEC, is one of the premier considerations. Article 240.87 indicates when designs should include arc flash reduction means and what the code minimum for differing systems in. Anytime there is a high continuous current trip setting for the overcurrent protection device installed in a breaker, and it is at or above or can be adjusted to above 1200 amps, it is going to be required to have arc flash mitigation. The NEC is the single most common standard used in the U.S. for industrial, institutional, commercial, residential, electrical design and installation. 110.16 will give us the marking requirements, while 110.21b gives us the information that is required to be on these markings. The NESC handbook, which is published by the IEEE, this reference standard is typically used in utility and public power distribution and installation for operation and maintenance of our electrical supply system. IEEE 1584 2018 edition is required for arc flash calculations and tells us how these calculations are guided and completed. NFPA 70E is the standard for electrical safety in the workplace. This assigns responsibility for employees and employers for arc flash safety, specifically when de-energizing equipment is not an option. This standard gives the required procedures for work protection, for PPE, and Annex D gives us the incident energies and arc flash boundary calculations methods, which are actually calculated off of IEEE 1584. While not a code, it is enforceable by OSHA. This is a standard that will typically go a long way towards compliance with OSHA requirements when setting up and managing your safety program. And with that, I will turn it over to Zia.
Thanks, Tracy. Let's one step back and look into what is the typical arc flash project approach. what we need to do as far as the steps. First, client meeting, field data collection, model development. Let's talk about the client meeting. It's so important. I always encourage people starting any project, discuss with the client, determine the approach or what they're actually looking for, what they want out of this project before spending time and money. And at the middle of the project, then you have to start all over again because you guys didn't make a right decision to what to do to beginning. Therefore, this is so emphasizing on that point. System study, short circuit, coordination, arc flash at the end. Therefore, those are the process study that we typically do. Now, at the end, next, result, create labels. We always trying to do for existing system, create a label and result based on the existing system, protect device setting and actual field data that is available, what we call it as built condition, and then including mitigation approach. The main discussion today would be system, including mitigation. I will go through several mitigation approach that I have written here to discuss. We may have more, but here a general type of approach that I like to discuss today with the short time that we have. The first one, de-energizing equipment, as we all know, most straightforward approach to eliminate the arc flash hazard. Of course, we need to make sure that we do proper practice, such as log out, tag out. The downside may be because you have to de-energize the equipment, downtime, costs related to this time. And in some cases, you really cannot de-energizing some safety-related equipment that has to be operating all the time. Therefore, however, that is the most straightforward mitigation approach. And we always have practiced that if the incident energy is so high, we don't have choice sometimes to select the first approach as you see here. Remote work or remote racking circuit breaker or close switchgear remotely, that causes increasing distance for the flash boundary and of course improve the personal safety. Again, if it's possible, maybe sometimes cost related and other issue related to this approach. Again, you need to have a system in place for doing that. Personal protective equipment, which typically that's part of the arc flash study anyway. I will discuss when we get to these steps. At the end, you selecting your PPE, and based on that, you performing the maintenance, working on energizing equipment. Therefore, PPE, based on the latest IEEE standard, which I will explain that again at the end, you will selecting based on the energy calculation, instant energy calculation, and be ready for proper PPE. This is one of the mitigation approach, which I don't typically recommending to, okay, if you have a PPE, then everything should be fine. That would be part of the mitigation approach, but this should be kind of in parallel with the other approach and technique that you will select for your facility. Training and planning. Again, this is really important because most people, maybe some people at a facility or the owner of the facility or personnel may not have enough education of this type of approach. They may not involve or aware of the costs related to this approved safety or improving safety in their facility. Therefore, again, I encourage that before we do any advanced mitigation approach, or discuss with the client to make sure they are okay with it. Because again, every of this approach that you select is corresponding with the cost for the owner of the facility. Therefore, we want to keep in mind that this should be considered in the beginning of any activity to make sure this is something that they're comfortable with. At this point, I will pass it to Tracy to adding more to my discussion.
Thank you, Zia. And I would like to focus specifically on healthcare and mission-critical considerations. These also do apply to other areas, obviously. These can include data centers, laboratories, hospital, freestanding EDs, amongst others. The number one thing that we must assess for these facilities is what is the likelihood that employees or guest employees, which would be contractors, will actually be required to clean, take readings, or interact with energized equipment. Typically, we'll find that this is extremely high because in these facilities, you can't have an entire shutdown just to walk in and clean the room or clean near the equipment. Next, we must assess systems that are critical to the operation. While everybody instantly would go directly to the emergency power supply system, or EPSS, we've actually found in studies that the normal power supply system is actually a critical piece of operations and life safety. We want to look for single fail points. ATSs or automatic transfer switches can actually become one of these single fail points where people will need to interact and potentially could have to interact with an energized system. What is the equipment that will have to be turned on and off for service? We're talking about AHUs, pumps, things of this nature that just by the nature of the equipment is going to wear out and is going to need service. Then we need to take a more holistic approach of what harm could happen if a main gear, whether it be the normal power supply system or the EPSS, were irreparably damaged. This could cause, in the case of healthcare, could cause diversion. It could cause loss of life in the case of any building. And also you could have to deal with the lawsuits and the repairs to the building that would go from there. How PPE affects maintenance. We actually get a chance to determine while we're looking at these systems and building these systems, how PPE will affect maintenance over the lifetime of the building. NFPE 70E tables method typically require bulkier clothing for gear with activities that have potential higher incident energy. When you are donned with full PPE in a hood, coveralls, or coat and pants, any activity that you take on takes a much longer period of time for you to be able to complete that activity. Again, the NFPA 70 charts will almost always err toward higher levels if an arc flash study has not been completed. So there is a long-lasting effect of not having an arc flash study. With that, I'll turn it over to Zia to get us into our mitigation techniques.
Okay, mitigation approach, and continue on that, changing existing PD type and settings. It is possible to make a decent reduction, can reduce fault clearing time, and of course, reducing the instant energy at the same time. Possible issue with this one may be miscoordination in some cases, that we have to either sacrifice the coordination or the reducing the instant energy, which I never recommend that, and no one that will recommending on sacrificing any coordination to bring the reducing instant energy. Continue on that one. I have several simulations during my discussion that we'll discuss through next several slides as far as the power system analysis and how we're able to reduce such based on the settings. Now, the following is a facility which concerns with the 4 kV system and 480 volt. There are 2 paths on utility injecting to this facility with 2 backup gen. Right now, I'm trying to emphasize on protecting the transformer, 1000 kVA transformer, by the fuse. Therefore, let's see how easily we can, using advantage of the set point, to reduce the incident energy. Therefore, if you look at in this TCC, I'm looking into the fuse protecting the transformer. As you see here, the fuse is rated 200 amps, and it's protecting the transformer, but I am still able to move or adjusting this fuse to take advantage of the settings to reduce the incident energy. Let's look at the results based on what I have. At this point, based on 200 amps fuse at this bus, I have I have 7.5, let me see here, 7.5 calorie, and next one, I'm going to move the fuse to make it 150 amps, and then I will reduce that one to about 3.35 calorie per centimeter square. The next approach would be a mitigation approach based on the current limiting fuse and fast acting fuse, which we're able to utilizing this one in the short circuit for more reducing the time delay. It may be difficult. Again, one of the problem with that one would be the PD that coordinate with the other devices utilizing this current limiting fuse. The next approach is the arc resistant switchgear. Something I need to point out that arc resistant switchgear reduces the amount of energy. It cannot be determined, the effect cannot be determined. The arc flash energy study, in arc flash study, you cannot determine this impact. You should know that the arc resistant switchgear, it does not reduce the electrical energy stored in the circuit. What it does, it gives you what the capability would be, what you need to do, determine the energy based on your system, compare it against the rated value for this type of switchgear. Therefore, the point I want to make here, it does not reduce the electrical energy stored in the circuit. It will you need to compare it against the rating that the manufacturer provided to you and based on the energy that you calculate in your system. The next approach, maintenance, I'm sure most of you may be utilizing that before. This can be in both LV and medium voltage system. The intention here to reduce the fault clearing time. It can be used at the control at the breaker or remote. Again, one of the issue with this approach may be miscoordination, because during this time, you're not going to have a coordinated system. Therefore, you need to be careful during this time, having a procedure and approach in place to make sure this will not causing any issue in the system. At this point, I will pass it to Tracy to continue my discussion with the sample of their facility and from that.
Thank you, Zia. Some of the considerations that we need to work with on maintenance mode considerations is that there will be additional training required for personnel for use of that system. It is not a hands-off system as others might be. The gear can get left in a maintenance mode if we don't have some type of BMS connections, or if we don't have a procedure for ensuring that gets taken care of. Also, a lot of the times we have a situation where our remote controls are at entrances of rooms for safety considerations. So therefore, we need to very much consider lockout tagout if these types of remote controls are used. And we must remember when we're working with maintenance modes that this equipment is still energized. We will still have to have PPE involved. We just have a much lower level of gear, which will be more simply worked in, but we do still have energized gear that we are dealing with. And with that, I will pass it back over to Zia for him to take us into our next mode.
Thanks, Tracy. Next, zone selective interlock. We can apply this for LV system in maintain electrical system coordination, and of course requires some wiring control of physical connection. It becomes really these days famous because the reason that I'm going to discuss. Before I go to more detail, let me give you some example what we trying to do with ZSI. ZSI helps to reduce sense and energy, in the same time help for system coordination. The picture that you see here, the incoming breaker and the feeder breaker with no ZSI. Typical coordination, we all as engineers, what we do, make sure the coordination exists. Now we're trying to make a coordination, which is fine. We have a coordination. Now let's look into instant energy for this system. This is the incoming breaker to one of these feeder. Now, based on the information, the calculation of instant energy at this point, the instant energy for this point is based on almost 0.33 seconds, is 15.7 calorie per centimeter square. Because remember now we try to coordinate this incoming with the load feeder breaker to make sure the coordination exists. In the same time, we are penalizing ourselves, which again, we don't have choice, by almost 33.33 seconds time delay FCT for getting this instant energy. Now, let's continue. By utilizing ZSI, what we can do, we can control or control the incoming breaker. We can enable the circuit breaker instantaneous, and at the same time, restrain signal from the load circuit breaker causes that we are okay on the incoming breaker instantaneous. Therefore, the instantaneous portion of the incoming breaker now has enabled, since the restrained signal from the load circuit breaker is preventing from the tripping on instantaneous on incoming breaker by almost, I put it for 250 milliseconds. Therefore, let's see the result. Now, the result, as you see here, we reduced from 15.7 calories per centimeter square to much lower, to 2.38. Now, the FCT time is 0.05. Therefore, we are reducing the instant energy at the bus because we were able to maintain the coordination by delay 250 milliseconds. If there is a fault at the load side, even though the incoming breaker instantaneous is enabled, if there is a fault and the feeder breaker, that causes that we still have the time delay that we put it there, which is here 250 milliseconds, to causing that having coordination and at the same time reducing the instant energy. Therefore, if you look at this system here now, if there is a fault at the load side and the breaker on the load will be tripping first, then incoming breaker by 250 milliseconds later, and then of course on the primary side. This model is being utilized, ETAP is being utilized for performing this model development on this picture right here. All right, now I pass it to Tracy for, again, continue my discussion on this topic. Thank you.
Appreciate that, Zia. Zone selective interlock is typically considered a more hands-off way of looking at arc flash mitigation. You don't have issues as you might have back with maintenance mode, where somebody could accidentally walk off and leave the system in maintenance mode. However, there are several things that are required to be looked at as you're putting the system together. It is more highly advanced engineering intensive, because your entire setup has to be engineered prior to the gear being built. Due to the internal wiring setups from the factory, it also requires advanced pre-planning, as these cables and this wiring is already built from the factory and sent with this gear. If there is a change at some point in time during the construction of the project and the sections of the gear need to be switched or moved in the field, this is going to require a factory field engineer for any kind of corrections, startups, or issues. You can also get zone selective interlocking that does have communications connections with systems, so therefore you can follow along and see how your system is doing. It will report back to your building management system. But this is an issue because if you lose that communication, you may not know that your gear is offline. Next to series-rated gear, this has one of the highest considerations that need to be taken for future additions or modifications once the system is completed. With that, I'll go ahead and turn this back over to Zia and let him pick back up on the next section.
Continue on mitigation approach. This is the last one I have, light detection relay. Again, this is another one that becomes famous now. Typically applicable mainly in medium voltage system. There is definite operating time, and the fault, arc fault can be clear and extinguished less than around 4 milliseconds, or again, that's just the bulk number, maybe different. Need to have both overcurrent and light detection to operate and detect. I have another simulation here for you. Let's assume we are trying to apply this one into our 4 kV, 4.16 kV switchgear A, and we're trying to look into how impact it's going to have. At this point, with before light detection approach, if there is an arc or fault at the switchgear A, I will have instant energy around 7.5 calorie per centimeter square. The fault FCT is about 0.75. Now, the way we can look into it, how we implement it, realistically at this point, I have not seen any software that be able to the same thing that I showed you on DSI, implementing it directly. However, we are able to utilizing the fixed time for this approach. Let's assume the light detection takes just a conservative number like 10 milliseconds. Therefore, if we assume on this bus here, the switchgear A, the fixed FCT is about 0.01 seconds. Therefore, that's the way we're able to achieve and implement this approach for time being for now. And as you see, the result for sure, since we are bringing the FCT lower from what we already had, 0.75 to 0.01, now we are reducing the instant energy from 7.5 to 0.1. Therefore, again, typical application maybe in medium voltage, and also, again, effective way to reduce the arcing current, arcing FCT, and consequently the instant energy. Therefore, that was the several mitigation approach, again, based on the time that we had. I'm sure there are a few more, and that's what we had for today.